Assalamualaikum. Hi. So this is a video presentation for my final year project 2 with the title of Design of an Integrated Hydrogen Preheater and Thermoelectric Generator Waste Heat Recovery System for Hydrogen Closed-Cathode Fuel Cell Mini Vehicle. My name is Muhammad Hamim as a student handling this project, and Prof Madya Dr. Ahmad Najmi Mohamad as my supervisor. Proton exchange primary fuel cell, or PEMC, is just one of hydrogen fuel cell types that generate electrical power from electrochemical reaction between hydrogen and oxygen. So closed cathode, or also known as liquid cooled PEMC, is suitable to be used for higher power usage such as in mini vehicle. So one of advantages to use PEMC is the ability to operate under low temperature below 100 degrees Celsius. However, its operating efficiency also recorded low at 50%. So this opens up opportunity to improve its overall operating efficiency. So to improve its efficiency, implementing waste heat recovery concept seems like a viable option, since under the exothermic reaction occurs in fuel cell, it generates sufficient heat energy that can be recovered. However, PMC only produce low temperature waste heat, okay, which means this has become the one of the challenge in maximizing the effect of recovering waste heat. Thermoelectric generator, or TEG, on the other hand, able to overcome this issue by directly convert heat energy into electrical energy under the seebeck effect. So TEG is just a series of N and P type semiconductors being clamped together. So by applying heat on one side and let cool on the other side, so this create temperature difference that will generate potential voltage. So the higher temperature difference, the bigger potential voltage generated. And also an experiment had been done and proven whereby preheating hydrogen able to increase the power output and its efficiency. So as stated in ideal gas law, increasing temperature at constant mass and volume will increase its pressure. So therefore, this will enhance the production rate of free electrons and also increase the output voltage. This project is about designing and analyzing integrated heat recovery, or IHR system for PEMC, as roughly shown in the figure here. So this system will recover waste heat from stack or fuel cell to preheat hydrogen, and also transfer heat across TEG modules to produce electrical energy. So heat exchanger has become the central part of this system. So objectives that need to be achieved from this project, which include developing IHR system for closed cathode PMC for mini vehicle usage, and to analyze its performance under different operating conditions. Project methodology in this study can be divided into two phases. The first phase is focusing on the design process of heat exchanger for IHR system. So firstly, we define our design requirement, where the design should be lightweight and compact, since it's being used for mini vehicle, and also able to be used for liquid and gas medium. The next, we define the design target for this system, which is it's able to recover at least 10% of total waste heat produced by fuel cell, and also it increase the hydrogen temperature by 15 degrees Celsius. The design codes and standard that we follow closely in designing the heat exchanger is ASME 8 Division 2 to be precise, and International Standard IS 4503. The design method that we use to determine the geometric sizing is log mean temperature difference, or LMTD method, that will tell us how much heating surface area is required, and we do cross-checking between assumption and actual overall heat transfer coefficient U to verify the design. This is the preliminary design of heat exchanger for this IHR system. It is essentially a counterflow shell and tube heat exchanger, where hydrogen as the cold fluid will flow inside the tube, while coolant as the hot fluid will flow within the shell or inside the shell. So this design consists of 10 2 inches tube that will for hydrogen to flow, and able to fit 30 TEG modules, 15 each on top and bottom, where it clamped together with heat sink plate to enhance heat removal process. So material that we use in this design mostly are aluminium. In the second phase, we focus on analyzing the performance of heat exchanger of this system. So we use both analytical and numerical method, where the result will be compared together. So the result from this analysis should provide us the estimated hydrogen preheated hydrogen temperature at different hydrogen flow rates, and the temperature profile at top and bottom side of heat exchanger, which the data can be used for future study. So the analytical method suitable for such tasks is effectiveness NTU method, where we're able to define the effectiveness of this heat exchanger in preheating the hydrogen based on its geometric design. So also the result from this method we can use to calculate how much waste heat being recovered using such equation. For numerical method, we chose ANSYS 19.2 CFD software with fluent code to help us with this task. The first step, what we call as geometry, which is we export CAD files into ANSYS and define our 12 bodies, which 10 of it for tubes and the other 2 for hydrogen and coolant fluid domain. The next step, what we call as meshing. So in this, we select proper contact surfaces and we define our name selection for all bodies, and we select automatic meshing at medium smoothing level, the aspect ratio just below 2, and the average skewness level at 0.2. So this shows the quality level of our mesh. The next, we move on to the next step, what we call as setup. So in this stage, we switch on the energy equation and we select standard K epsilon model as a viscous model with standard wall functions. So we assign material for each cell zones and we couple every necessary mesh interfaces, and we define our boundary condition also in this stage. So the final stage before proceed to result is what we call solution. So we stick with the default setting, which includes simple method, least square cell base, second order for pressure, momentum and energy, first order for turbulent kinetic and dissipation rate. So the convergence criteria also had been set at default settings. The first result that we would like to discuss and analyze is the fluid flow streamline for coolant and hydrogen. So these results are based on flow rate of hydrogen at 0.005 kg per second. So the first one is the coolant flow. So as you can see, the flow of coolant spread evenly throughout any gaps between tubes in the shell side. So this benefit the distribution, uniform distribution of heat across inside the shell of the heat exchanger. Different pattern can we see for the hydrogen, where the hydrogen only majorly flow in the 2 tubes located in front of the inlet and outlet of the heat exchanger. So this result in poor utilization of available heating surface area, which can affect the final output of the preheated hydrogen. So this can be improved by modifying the geometry design of the heat exchanger. Next result we shall discuss is the temperature counter across heat exchanger. So as we can see, the temperature counter match with other related research that been done on counter flow shell and tube heat exchanger. So based on section view AA, it shows how the hydrogen coal in the inlet being warmed up as it approaching the outlet port, and section view BB shows how the coolant entering heat exchanger at high temperature being cooled down as it passes out tubes. So this result successfully display on how heat energy being transferred from hot fluid to cold fluid. To evaluate how the heat being supplied to all TEG modules, we shall study and discuss the temperature pattern on top and bottom side of the coolant medium. So here we plot 6 locations where the local temperature are being recorded and analyzed using this graph here. So similarly, at all hydrogen flow rate as the changing variables, the temperature ranging from between 52 up to 58 degrees Celsius at all 6 locations. So this small temperature gradient across all locations shows that how the heat is evenly spread across heat exchanger, and which help in providing uniform heat supply to all TEG modules that had been laid across heat exchanger on top and bottom panel. So in addition, this will help in producing a uniform electrical power output by all TEG modules. So the next result that we shall discuss is we comparing between analytical and numerical result of preheated hydrogen temperature that we predict at different hydrogen mass flow rate. So based on this figure, we can see that a declining pattern, okay, on the hydrogen outlet temperature as the hydrogen mass flow rate increase. So the question should be asked, why at higher flow rate of hydrogen result in lower outlet temperature? So based on the method that we chose in predicting the outlet temperature, which is the effectiveness NTU method, the outlet temperature or the result, the output, it really mainly depends on the NTU, the number of transfer units. So this NTU, dimensionless NTU, is actually inversely proportional with the fluid mass flow rate. So which explaining why at higher mass flow rate will result in a lower number of transfer unit, which then result in lower outlet temperature. So this also affect the hydrogen temperature difference across between the inlet and outlet of the heat exchanger at different mass flow rate. Okay, so for this design, we has defined that we target to reach the increment of hydrogen temperature by 15 degrees Celsius. Okay, so based on the analytical, we able to reach between 16 to 20 degree Celsius of increment, while in analytical the maximum that we can achieve only at 14 degrees Celsius. So this back to the problem that issues that rise, which is the poor utilization of heating surface area. Okay, so by improving the geometric design, will improve the hydrogen flow rate, the hydrogen fluid flow for flow stream, which can enable us to reach the design targets. Lastly, we would like to see on how much waste heat being recovered based on the waste heat produced by the fuel cell, okay, based on analytical and also numerical. So for this design, we target at least 10% of waste heat produced by fuel cell being recovered. Okay, so by analytical, we are able to exceed the target greatly, okay, by recovering the heat 16 to 20 degrees Celsius. But for simulation, it dropped a little bit, but still able to exceed our estimation by recovering the heat between 12 to 16 degrees Celsius. 16%. So this shows that the design is able to meet our design target in terms of waste heat recovery percentage. So in conclusion, the IHR system able to be in conclusion, IHR system are successfully designed and analyzed using various methods. Okay, so based on our study, okay, we found out that the development of heat exchanger design able to improve hydrogen fluid flow, and also the temperature profile across heat exchanger match with other existed, okay, counterflow shell and tube heat exchanger studies. Okay, and the average temperature across top and bottom side of heat exchanger recorded at 54 degrees Celsius, which can be used as the data input for future TEG study. And based on this design, it able to by simulation, we able to increase hydrogen temperature by 11 to 14 degrees Celsius and recover the waste heat from fuel cell about 12 to 16%. So the comparing between analytical and numerical, we saw similar output pattern between these two methods, okay, with only marginal difference between 7 to 12%, shows how the validity level of our study. So there are some recommendations that can be implemented in the future study. The first one is to minimize the number of tubes for heat exchanger, and the second one is to design that will ensure hydrogen to flow in a single tube rather than multiple tubes at one time. Okay, and next is to expand the range of hydrogen mass flow rate as in the studies to increase the accuracy for this study. And finally, to simulate the whole IHR system, okay, which includes preheating the hydrogen at the same time providing heating for the TEG side. So this will evaluate how the heat exchanger behave under different operating condition. So that's all from me. Thank you.